Hello everyone, welcome Dr. Kirsten here for your present today. It's my pleasure to be here presenting about building RISC-V based accelerator. My full Vietnamese name is Phạm Nguyễn Hoàng Hải. It's quite hard for non-Vietnamese to pronounce, so globally you can call me Henrik or Hải. So let me introduce myself. I completed my bachelor degree in computer engineering in Vietnam. The story of my life is about a bottom-up story. So during my internship at Renaissance Design Vietnam, our team maintained the AutoSAR MCON. It stands for the Automotive Open System Architecture, and MCON stands for Microcontroller Abstraction Layer. My first full-time job was as a software engineer, and our client was Renaissance Design Vietnam. We supported their Japanese and German team in implementing a loosely timed virtual platform for the Aka V3U. When I examined the virtual platform source code designed by German engineering team since 2000, I was impressed, but I didn't think I have a chance to come to Germany at that time. I was curious about the potential of ARM cores beyond the embedded world that I joined Ampere Computing. It's an American startup that builds ARM-based CPU for cloud servers. Our team designed the system-level testing framework for the fab in Korea to stress test the chips for chip binding. Then we ship the chips to our customers like Google, Microsoft, Amazon, Gigabyte. Later, I pursued my master degree in Taiwan, where I worked closely with my supervisor, Peter, to deliver most of our industrial collaboration projects. He eventually referred me to ITI, which gave me the opportunity to pursue my PhD here since last year. That's quite a lot about myself, so let's move on to exciting insight from my work. RISC-V is a promising open standard for designing and implementing central processing units and their co-processor. Why is it promising? Because we now have an open instruction set architecture which defines the interface between software and hardware. Whether your software is open source or proprietary, it can be compiled into binaries using an open source compiler targeting the RISC-V architecture. You are no longer dependent on a specific CPU licensor, like ARM or vendor, as long as their RISC-V CPU products pass the instruction set architecture regression test. Your program can run on any RISC-V CPU implementation. RISC-V also benefits academia thanks to its design principle, simplicity, modularity, and openness, allowing us for flexibility and customization. On the left is CPA6 by ETH Zurich. A state-of-the-art RISC-V core is like a giant offering his shoulder for us to stand on. CPA6 supports both 32-bit and 64-bit designs, and a reference custom accelerator design in the execute state of the CPU core. It allows us to build our own RISC-V-based accelerators or system-on-chip targeting performance or energy efficiency. On the right is ARA, also from ETH Zurich. It's a co-processor for CPA6 that vectorizes computing operations. This state-of-the-art design offers valuable insights into building extremely high-performance co-processor. So how can we do it? I mean, building an accelerator for RISC-V. Let me give an example. We are building an accelerator for Kyber, a key encapsulation mechanism designed to resist attacks from future quantum computers. A210 development board is an ASIC RISC-V product, a real physical RISC-V product. By profiling Kyber on K210, we obtain the number of executed instructions and the elapsed clock cycles for each function. Using a quantitative approach, we gather statistical data that help us generate questions, ideas, and potential solutions. For example, I put some note and some tasks here when I examine the benchmark result for Kyber on K210. I also want to introduce one of the seven great ideas in computer architecture to make the command case fast. So with the profiling data, we identify that the number theoretic transform with use ready-to-use operation is compute intensive. This led us to the idea of designing a custom instruction for RISC-V that connects to hardware acceleration for Redis 2. Emu, an open source virtual platform, allows us to quickly prototype our custom instruction by implementing a virtual custom instruction for Redis 2. We observe that a reduction of up to 39% in executed instruction compared to using the base RISC-V instruction set. Our current step is implementing hardware to execute the Redis 2 operation. This accelerator will be functionally validated using golden data from the software. Then we will estimate its cycle count using Verilator, an open-source tool that synthesizes our custom hardware design into a cycle-accurate simulation model. After that, we will implement the design on an FPGA to emulate it at a physical logic level and fine-tune the timing. Finally, the product will be ready for the massive ASIC phase. I would like to end my presentation with an open question. Which function in industry like automobile, telecommunication, cryptography, aerospace, electronics, finance, and banking, etc. are what accelerating with custom hardware? Thank you.